Welcome, viewers, to the fourth segment of the seventh lecture for the online series of lectures for the course of differential geometry. We are going to begin this segment with the notion of rank of a smooth map. Recall from lecture 6 that the rank of a smooth map F between two manifolds N and M at the point P in the domain manifold N was defined as the rank of its differential at P. That is the rank of the linear map F star comma P from the tangent space TPN to TFPN. Now we'll study two situations related to the rank of a smooth map. Okay. One, when this F has maximal rank at P in the domain manifold N. 2, F has constant rank in a neighborhood of P in the domain manifold. Okay. Now, if F from N to M has maximal rank at P in N, then there are three mutually not exclusive possibilities. Okay. So, which means that there can be overlap between the cases. A, if N is equal to M, small n is a dimension of big N and small m is a dimension of big N. So in this case, we want the dimension of the manifolds, the domain manifold and the target manifold to be the same. Okay. So if this is the situation, then since F star P is a map from the tangent space TPN to the tangent space TFPM, since this guy is a linear map with maximal rank, okay, so we are exploring the possibilities for F having maximal rank. Okay, one must have a rank of this map f star comma p is equal to n equal to dimension of this tangent space TPN. Okay, so they're both the same, and n is equal to m. So rank of f star comma p is equal to m is equal to n, and n is equal to the dimension of the tangent space TPN. Okay, hence by rank nullity theorem, we know that kernel of this linear map f star comma p is equal to we know that the nullity of f star comma p is 0, right? And which means that kernel of f star comma p is just the zero vector of the tangent space TPN, yielding f star comma p is non-singular. Okay, the kernel is trivial means that the linear map is non-singular. Now, since dimension of the tangent space TPN is the same as the dimension of the tangent space TFPM, and f star comma p is non-singular, okay, one has f star comma p, this linear map is bijective. Okay, hence f star comma p is a bijective linear transformation. Bijective linear transformation, that is an isomorphism between these two tangent spaces TPN and TFPM. Therefore, by remark 1 to proposition 4 of lecture 6, f from n to m is this is locally invertible or a local diffeomorphism. It has another name, local diffeomorphism. At the point P in N. Okay. Good. Now the second case being n is less than or equal to m, then using the fact that rank at this f star comma p is always less than or equal to the minimum of m and n. Okay. One arrives at, since n is less than or equal to m, one arrives at rank of this linear map f star comma p is less than or equal to n. Since rank of f star comma p is maximal, the rank of this map is equal to n. Hence, by rank nullity theorem, rank nullity theorem of linear algebra, nullity of this linear transformation f star comma p is equal to 0. That is, kernel of this linear transformation is trivial, consisting of the 0 vector only. In other words, f star p as a linear map between the tangent space Tpn and Tfpm is injective. Injective. That is, f from n to m is an immersion at the point P in the domain manifold n. Okay, now the third case. For the situation when f is of maximal rank. C. If n is greater than or equal to m, then again, using the fact that rank of this linear map f star comma p is less than or equal to the minimum of these two numbers m and n, one obtains a rank of f star comma p is equal to is actually less than or equal to m, and by maximality of rank f star comma p, one has rank f star comma p is equal to m. That is, image of this linear map f star comma p is m dimensional, right? But hence f star comma p, which is a map between the tangent space TPN and TFPM, is surjective, right? So the target space, the codomain of this linear map f star comma p is this tangent space which has dimension m, and the image of f star comma the image of TPN under f star comma p is also m dimensional, okay, which coincides with the codomain of this linear map, which means that this map is surjective. In other words, F is a submersion at P in the domain manifold. Okay, now we need the constant rank theorem for manifolds. I think we discussed constant rank theorem in the context of Euclidean spaces at the end of lecture 2, but we at this stage need the constant rank theorem for manifolds, so I'm stating it. Constant rank theorem, I'm stating it and then I'll prove it. Constant rank theorem for manifolds, which is theorem 3 of the 7th lecture. Let n and m be manifolds of dimension n and m respectively. Suppose f from n to m has constant rank k in a neighborhood of a point P in N. There are charts U comma phi, then I should say then there are charts U comma phi centered at P in N, that is phi of P is equal to the zero vector in the Euclidean space R to the N, and V comma psi centered at f of P in M, such that f of U is contained in V. So let me explain what it means. So V comma psi is centered at Fp in M, means that psi of f of P is equal to the zero vector in the Euclidean space R to the M, such that for R1, R2, all the way up to Rn in phi of u, right? Phi of u is a subset in the Euclidean space R to the n, right? And a point in the Euclidean space R to the n is given by this n tuple, right? R1, R2, all the way up to Rn. Now, psi composed with f composed with phi inverse evaluated at this point R1, R2, all the way up to Rn, which is a point in phi of u, is going to be equal to R1, R2, all the way up to Rk, okay, where k is the constant rank k of this smooth map in a neighborhood of a point P in N. Okay, so the first Rk coordinates are non-vanishing and the remaining ones are vanishing. That is, there are m minus k many zeros here. Okay, this is going to be an m tuple in the Euclidean space R to the m. Okay. Okay, good. Now I need to prove it, so let me erase everything and prove theorem 3. Proof. Choose a chart u bar, comma, phi bar about P in N and V bar, comma, psi bar about F of P in M with F of U bar contained in V bar. Okay. Then psi bar composed with F composed with phi bar inverse is a map from phi bar of U bar being a subset of R to the n to psi bar of V bar being a subset of R to the m is a map between open subsets of Euclidean spaces. Okay, so phi bar of U bar is an open subset of R to the n, and psi bar of V bar is an open subset of R to the m. Because psi bar and phi bar are diffeomorphisms onto respective images, okay, the pertaining differentials are isomorphisms of vector spaces, right? Isomorphisms by remark 1 to proposition 4 of lecture 6. That is psi bar star comma f of p okay, and phi bar inverse star comma phi of p are both vector space isomorphisms, are both vector space isomorphisms. Also, psi bar composed with f composed with phi bar inverse star comma phi bar of p is equal to psi bar, okay, let me start from the far right, phi bar inverse star comma phi bar of p composed with f star comma, okay, so phi bar inverse acting on phi bar of p is going to give us just p, okay, and that composed with psi bar star comma, so f acting on p is just f of p is by the chain rule, okay. So this is equation number 10. Now it is indeed a simple linear algebra exercise to check that composition with isomorphism from both sides does not change the rank of a linear map. Okay, so it's a very simple exercise. Do it. Hence, a rank of this composed map, psi bar composed with f composed with phi bar inverse star comma phi bar of p, is just the rank of this middle map, rank of f star comma p. This is equation number 11. Now, rank f star comma p is called the rank of this smooth map smooth map F from N to M at P in N, we see from equation number 11 that the map psi bar composed with F composed with phi bar inverse between open subsets of Euclidean spaces also has constant rank K in a neighborhood around phi bar of P in R to the N. Okay, so it's because F star comma P, it's because F has constant rank K in a neighborhood of the point P in N. Okay, now by the constant rank theorem that we stated at the end of lecture 2, by the constant rank theorem for Euclidean spaces, discussed at the end of lecture 2, there are diffeomorphisms. There are diffeomorphisms I should write there are a diffeomorphism G of a neighborhood of phi bar of P in R to the N, and a diffeomorphism H of a neighborhood of psi bar composed with F at P. In R to the M, such that H composed with psi bar composed with F bar inverse composed with G inverse at R1, R2 all the way up to Rn is equal to R1, R2 all the way up to Rk, and the remaining ones are zeros, so there are m minus k many zeros here, right? Because on the right hand side I have an m tuple. This is equation number 12. Okay, now we set H composed with psi inverse to be equal to psi, and G composed with phi. So H composed with psi bar is psi, and G composed with phi bar is phi, to obtain psi composed with F composed with phi inverse at R1, R2 all the way up to Rn is equal to R1, R2 all the way up to Rk, comma 0, comma 0 all the way up to 0. Okay. Now I want you to check that phi of p is equal to g of phi bar of p is equal to the zero vector. Remember, phi of p was the zero vector in R to the n. Okay. No. Let me check. So let me go back to the second lecture to check the constant rank theorem between open sets of Euclidean spaces. So G of phi bar of P is equal to 0 by the constant rank theorem between open sets of Euclidean spaces, right? So right. Okay. So G of phi bar of P is equal to 0. Hence phi of P is equal to the 0 vector, right? And also H of psi bar of Fp, f of p, okay? H of psi bar of f of p is equal to the zero vector in R to the n, and hence this is the same as psi of f of p, right? Right. So indeed, we found that phi of p is the zero vector in the Euclidean space R to the n, and psi of f of p is the zero vector in the Euclidean space R to the m as required. QED. Okay. Good. I think I'll take a break here, and we'll be back with more results like constant rank level set theorem in the 5th segment of the 7th lecture. Thank you for attending the 4th segment of the 7th lecture.